We'll start to look at the concept on diffusion flame, diffusion burning. As I explained earlier, candle flame is the typical diffusion flame, and we just explained those combustion characteristics of candle flame basically controlled by the diffusion transports. For example, the fuel diffusion and the oxygen diffusion will give those reactants meet together at the position of a diffusion flame. And after the chemical reaction, heat will release and diffuse out from the diffusion flame to the both sides of one is the fuel side and the other one is oxidizer side. The product has a similar way to diffuse out of the diffusion flame. And this flame structure is explained earlier and shown in the slides of let me see the page 1.34. I mentioned here the basic definition for diffusion flame is this: reactants are initially separated by the flame itself and stoichiometry burned at the flame. You should remember stoichiometry burning for diffusion flame is not the same as the burning defined for premise flame. For premise flame, we have a so-called, because they are premixing of the fuel and the oxidizer. Then from the initial condition, you can identify the lean condition, the rich condition, or stoichiometric conditions. Okay. And always at the position of premise flame, the burning status, except the stoichiometric burning. For example, for the lean burning, they will have extra oxygen exist in the reaction zones. For the rich case, you will have an extra fuel exists in the reaction zone. But for diffusion flame, both fuel and oxygen should be completely consumed at the flame position of the diffusion flame. Basically, if you think ideally the infinite chemical reaction rate, they should complete finish just at the position of the diffusion flame. But if you look at reality, the finite chemical reaction rate, you may have some leaking of the fuel to the oxidizer side and the oxygen leaking to the fuel side. I will give you some experimental observation to think about those kinds of leakage. And I emphasize three important combustion characteristics for a typical diffusion flame, which is which are the thin high temperature zone the diffusion flame has, and the high gradients of temperature and the concentration occurring in the neighborhood of the diffusion flame. And definitely the diffusion flame find its locations, not the balance of the flame speed and the supply velocity. Those balance of the flame speed and supply velocity is used for the determination for the premise flame positions. Okay, but the position of diffusion basically is determined by the balance of the fuel and oxidizer diffusion strengths. Okay, later on I will explain to you. Now I give you the next example. We are looking at the counterflow diffusion flame, or we call it a post-jet flow diffusion flame. I use one example is like this. You can see these pictures in the left-hand side. There is the fuel supply. Actually, this fuel supply is you can think of it. It's just like a cylinder, but there has a porous porous wall, and those porous wall means you can have some fuel coming in through the tube, and they will injecting out through the porous medium, and those fuel will inject two stream of the air coming from the lower part, and they're flowing upward to meet with the fuel inject out from the porous surface, and then meet together. You will have a so-called stagnation point flow. And this stagnation point basically is a counterflow because there is a two flow meet together, but the stagnation plane has a curvature. Okay, since the upper burner actually is a cylindrical shape, is a circular shape. then the penetration or injection of the fuel will go to different angles to meet with the outer air. And if you try to use the fuel meet with the air, in this case, the fuel in the examples, they use the propane. Okay, the propane meet with the air coming from the loader flow. When you ignite it, you can see this is the typical pictures. It's a both black and white pictures, but you still can see very clearly. Here there is they use the laser diagnostic, and the laser sheet will give you the string lines of the air. Okay, you can see as I described earlier, and this is the bright line represents the streamline of the particle going through the air sites. And here there is the bending. You can see there is the bending, right? And this bending tell you there is the stagnation plane exists here. But this stagnation plane is different from a previous one we discussed. When you use the two cylinder and to let the two jet impinging together, then you will have flat planar stagnation plane. But in this case, because the upper burner is a cylinder, therefore the stagnation plane is curved along with the circular shape of your cylinder. And here, when you ignite it, you can see this the white band, and this white band represents the blue flame you may have here. Okay, this is from the experimental observation. Now, we try to look at some flow structures and concentration distribution, also temperature profile for this propane air flame, and to let you know the combustion characteristic of the diffusion flame. In this case, it is clearly the fuel supply from the upper cylindrical burner and the air coming from the lower flow. Then the oxygen and the fuel are separate. Okay, and when the fuel coming from the top cylinder, oxidizer coming from the lower flow, they meet together to generate so-called diffusion flame. But this diffusion flame is quite close to the stagnation plane. Okay, now let's see. This the picture basically is for the propane air flame, but they did another experiment with the methane, and they give you some experimental results. And these figures show you the density and the strain to area ratio for a given methane flame. Here you can see the horizontal axis. There is the ADA. ADA, the definition for ADA basically is the position of the flame and also the position for the measuring point. Okay, here Z means the actual coordinates, and starting from the origin at the circular the cylindrical surface. Okay, 0 is the cylindrical surface, and they move to the lower flow continuously from 0 up to 6. Okay, and R represent the radius of the cylinder. Reynolds number is the flow you will the root corresponding to the lower flow, the air flow. Okay, and the simple way to look at the eta means the position of actual coordinates. Okay, when eta equal to 0 means that you are at the surface of a cylindrical burner. Okay, the upper burner. When you increase Z, that means that you move away from the surface of the cylindrical burner. And the left hand side, in the left hand side, in the vertical axis represent the density variation, and in the right hand side represent the strain tube area. What is the meaning of strain tube area? Actually, simply you just measure the diameter. Okay, for a given strain tube, because this is a symmetric flow, you measure the diameter of a given strain tube, then you can count the strain tube area, and you can see from the pictures the strain tube area will expand continuously when you approaching to the stagnation plane, okay, because there is the expansion. When the flow has an expansion closer to the stagnation plane, the closer area, the stream tube area will be increased, okay. Now let's look at the experiment results here. They in the plots they mention there is the stagnation plane here around 1.3 or something, okay, and you will have a friend exists very close to the 3. There is the luminous reaction zone. That means that you can see this friend here. Okay, now we look at first. We look at the stream tube area variation starting from earlier, very far away from the cylindrical burner. You can see the string tube is very small, okay, and you choose one small string tube, and those cross-section area will remain almost no change, constant until they move to very close to the floor. Actually, they start to go to the some temperature increase. Later on, I will show you the temperature profile. You can see when starting around here, the temperature in the flow is increased because there is some heat diffuse out from the diffusion frame. Okay, from the diffusion frame. Then you can see the stream tube start to increase. The area start to increase to a certain value, then they they go to, they stay at the position of diffusion frame. Actually, the stream tube do not change too much, but later on, they will increase tremendously as they approaching to the stagnation points. Okay, you remember the stagnation stagnation point regions or stagnation point of the stagnation plane represent the separation of the upper and the lower flow. Okay, the lower flow will expand to a large area when they approaching to the stagnation plane. Then that means the stream tube area will increase to very large value. Okay, and this is a typical flow structure for you to understand. And now we move to the density variation. From the beginning, actually, the lower flow contains air only. Air has a larger density compared with the methane coming from the upper cylindrical burner. The methane has a lower density. Okay, therefore, for the points at each side, right hand side and the left hand side represents the air condition and the methane condition. Air has a higher density compared with the density that of the methane. But when you start to move from the lower flow with the air, you can see the density almost no change until they are very closer to the diffusion frame. The density drop down. Why the density drop down? This is caused by the temperature increase. As you look at the ideal gas law, when you have a temperature increase, then your density will decrease. Okay, and this sharp change of the density decrease represents the high the sharp increase temperature gradient occurs in this region. Later on, I will show you. When they reach to the position of your diffusion frame, the density reach to the minima points. Later on, they will increase slightly again, okay, slightly, because now you have some products mixed with the fuel coming from the left-hand side, okay, then go to the to closer to the burner exit, then density will meet to the density of the purely methane. And here they still have some temperature influence on the density, but this is a relative weak. Okay, and I will let you know the temperature variation. You can see for the next pages. But this is the first part to let you know the flux structure variation for a given diffusion frame exists or located in the forward stagnation point flow. Now we go to the next part. Now we are looking at the concentration distribution for such a diffusion frame. The coordinate system described from 0 to 4 based on ADA definition is completely similar, the same as to the previous one. And here you can see they show you the mole fraction for different species in log scale. Okay, you should be very careful to read these plots. We start from the very far upstreams, the lower flow. Actually, you understand there is the pure air. For pure air, for the oxygens, for the mole fraction, they should be equal to 21%, right? 21% here is very closer to the 21%. And the rest of the gas in the air is nitrogen, is 79%. Okay, then you can see this is a typical composition for the air. But for the oxygen concentration, you can see from the outer flow when you approaching to the premise to the diffusion frame. Diffusion frame exists here. Okay, very close to eta equal to 2.9 or 2.8. Okay, oxygen drop to a small value. You should remember, because we use the log scale, even when you find out the oxygen at the diffusion frame positions, they are very close to the 10 to the power of -2. But this is show you a small value. But this is small, but the small values extend to the further regions closer to the diffusion frame. As you remember, I mentioned for the finite chemical reaction rates, they always have some leakage of the oxygen from the oxygen to the fuel side, right? From oxidizer side to the fuel side. Then you can see there's some small amount of oxygen left in the left-hand side. Okay, this is a so-called oxygen leakage. Now you look at the methane, similar way methane from the left-hand side, from the cylindrical burner, initially there is the 100% pure methane, then they do not have too much change, but they start to have some decomposition, then the concentration of methane reduced, continuously reduced up to when they close to the diffusion frame, to the oxidizer region, then they drop to the 0. Okay, this is the concentration of the fuel supply from the left-hand side and the oxygen supply from the right-hand side. And you can see they will meet together at the position of the diffusion frame and burn it. Okay, now we try to look at the intermediate species based on the decomposition of the methane. You can see the methane concentration decrease from the left-hand side when you approaching to the diffusion frame. At the same time, those intermediate species will be created because methane will convert to different kinds of intermediate species. For example, hydrogen is the major one, and also there is some C2H2, C2H4. Actually, those species are small value because this is a log scale. Actually, they may exist. The scale go to the 10 to the power of -3. It's very small amount. You don't need to care about it. But usually, you cannot measure the OH or HO or H2 or O reticles, those kinds of concentration, because they are too active. You need to use a laser diagnostic to measure it. But for the usual way to measure the concentration, typically we just can do the measurement on those stable species, for example, H2. But you can see there is an increasing concentration of H2 continuously to the maximum value in the neighborhood of a diffusion frame. And finally, they will drop down, okay, because those hydrogen will be burned completely. And you can see also there is a very important intermediate species, CO, carbon dioxide. Okay, they will reach to the maximum points very close to the position of diffusion frame, and finally they will drop because on both sides. For the left-hand side, because this represent the initiation of this intermediate species, the grow up. But the right-hand side tell you the depletion of the CO because they will react with the additional oxygen in the right-hand side, okay? And typically, you can see CO2 occurs, the development, and for the CO2 concentration, then you can see they will reach to the maximum point at the diffusion, at the position of diffusion flame. And a similar way, you can see this break, break circle symbols represent the concentration variation for the water, and then they reach to the maximum value at the position of a diffusion frame. And yeah, this is a very simple illustration to the concentration variation for diffusion frame. When you have a diffusion frame, oxygen coming from the in the product from the right hand side, methane coming from the left hand side, they meet together and then they react, okay, and then produce the maximum value for H2O and the carbon dioxide. And in this in the flow regions, they have some intermediate species grow up because the dissociation of a methane to produce those kinds of intermediate species. But definitely, those intermediate species will be complete consumed and convert to the carbon dioxide and water at the diffusion frame. And I want to point out from earlier description on the fuel and oxygen leakage to either side. And this is definitely you can observe from the experimental observation. This is due to the finite chemical reaction. You cannot finish all the reactions to convert the reactant to the products in a short, very nano region. Then you may have some oxygen leak to the fuel side, some fuel leak to the oxidizer side. Now look at the temperature distribution. Yeah, you can see very clearly here. Okay, in the upstream side, in the lower flow, you can see temperature is quite low. Here the temperature is K. Here is somewhere 300 K. That means it's a room temperature. And when they approaching closer to the diffusion flame, the temperature increase to a very high value up to the 1800 K. And in the left-hand side still, you can see there is the temperature gradient increase from the edge of the burner to the flame position. And this is just a typical temperature profile for a given diffusion flame. They tell you heat release, then the temperature jump to the highest one at the diffusion flame positions. Then those thermal energy will be diffused out for the air side and also to the fuel side. Okay, this is a typical temperature profile for a given diffusion flame. And here, I think that from this experiment, you can clearly understand the diffusion flame structure. I give you another example to make it clear and a comparison. Actually, they are quite similar. Let me try to change it a little bit. I'm sorry, you need to wait. Somehow you need to wait a little bit because I need to change the document to share with you. Okay, you can see it. I give you another example. Actually, the result is completely similar to the previous one. Now we go back to our previous system. I described we have a opposite jet flow, right? And this is the typical cold flow structures for the opposite jet flow for the stagnation point flow. But here we focus on the opposite jet flow, a similar way compared with the previous experimental observation. We try to impinge two different kinds of composition jet from the upper and the lower burner, try to look at the flow structures here. For example, this is a typical very nice experiment. And this figure tell you the flow visualization for the cold flow for the post-jet cold flow. But in this case, if you try to use the mixture of oxygen and nitrogen from the upper burner and use the methane mixed with the nitrogen from the lower burner. In this case, we do not use the pure methane because burner size is pretty much large. When you use the methane, you will produce too much. You will consume too much fuel. Okay, then we just try to mix a certain amount of nitrogen to balance with the upper burner, because when you look at the upper burner, they try to supply the oxygen and the nitrogen mixture, right? And the momentum relative are large, and you need to have some nitrogen coming from the lower burner to balance the momentum of the upper jet. So which means in this case, if you inject the oxygen mixed with nitrogen from the upper burner and inject the mixtures of methane with nitrogen from the lower burner, these two jets will impinging together, then they will produce the opposed jet flow. And this opposed jet flow, you can see their flow structure is from these pictures. Okay, this is a cold flow pictures. And because the oxygen coming from the upper burner, methane coming from the lower burner, they will meet together very closer to the stagnation plane. When you ignite it, you can see there is the blue flame here. Okay, and this position of blue flame, the diffusion flame, is very close, or we can see just sit at the stagnation point. Okay, stagnation plane. Now we do the measurement for temperature and the concentration along the center line. Okay, then you can see this is a Z. The position of your origin Z is located at the exit plane of the lower burner. When you increase your Z coordinates from 0 to, I remember, is 18, then you will reach to the edge of the upper burner. Okay. Now, we try to explain the first one. We try to explain the concentration variation for oxygen and the methane. The oxygen coming from the upper burner, right? Now you can see the upper burner here. The hand side show you the upper burner, the upper flow. The oxygen, I'm sorry, the upper flow should be corresponding to your right hand side here. Okay, then the circle symbol represents the oxygen concentration. You can see, you can read through it, it's 21%, right? Okay, 21%. For the methane, in this case, you need to read the scale for the methane, and the methane concentration profile shown in the left-hand side represent the lower flow. Here, methane is around 43%. I cannot remember, but this is because we already mentioned the mixture basically is a mixture of methane with nitrogen. Okay, now here you can see methane somewhere is 43%. But anyway, there is a methane coming from the left hand side, and there is oxygen coming from the right hand side. Initially, when they have some distance away from the diffusion flame, the concentration remain constant for a certain region, right? There almost no change here and almost no change here. But when they approaching to closer to the position of diffusion flame, for the location of diffusion flame is around 9.9 millimeter here, very close to 10. Okay, then you can see the oxygen concentration dropped tremendously to some certain small value, but they still leak to the fuel side. Similar way, fuel methane will drop very fast, and this steep gradient give you the small value at the position of the diffusion flame. However, they still keep a certain small amount of methane until to a certain position in the oxidizer side, they completely finished. Okay, and this is another evidence to let you know there is the fuel and oxygen leakage occurs in the neighborhood of a diffusion flame, and you at the same time you can see there is the very similar plot for the temperature profile and also the carbon dioxide concentration. They are very similar because when you finish the chemical reaction at the diffusion flame, they will release heat to make your temperature to reach to the maximum value, and all carbon dioxide as the products reach to the maximum value, and they have a similar way have a thermal diffusion to let the thermal energy diffuse out to both sides, and carbon dioxide will diffuse out by mass diffusion to both sides. Okay, and you can see this is the typical flow, typical temperature profile and a concentration profile for a given diffusion flame. This experimental result is complete, can be complete, similar to the previous experimental result I introduced you based on forward stagnation flow, the counterflow structures.